Hello and welcome to another edition of Ontology Talk. I'm Adam Pease, and today I'm going to talk about contradictions and modeling choices. So let's say we have a fairly simple and obvious sort of contradiction, two bits of knowledge that oppose each other. John's car is blue and John's car is not blue. Very straightforward. In logic, we might, in a propositional logic, for example, we might assign these symbols. So John's car is blue is the symbol P, and John's car is not blue is the symbol not P. And obviously you can't have both at once, right? That's a contradiction. P and not P oppose each other. It's not possible. And so this is one of the most basic things that anyone learning mathematical logic will start with in an introduction. And the message usually from the instructor is that contradictions destroy a logical theory, at least in classical first-order logic. Now, what do we mean by that? In a classical logic, it's a two-valued logic, logics that have only true and false. There are other logics that maybe have true, false, and unknown. But for a classical logic, we're talking about it's just either a statement is true or it's false. And first order logic. So this is going to be maybe a little mysterious if you haven't already had a course in logic or some background there, but try to summarize it by saying a first order logic is quantification over terms, or you could also think of that as the things that you can relate to one another must be terms rather than truth values. So let me give you some examples of that. And I have a prior video on the difference between truth values and functions and terms and so forth. So I'll give you a link to that for a little bit of expansion. But just briefly, there are statements that have truth values, like Boston is in Massachusetts. That's true. Italy is in South America. That's a false statement, but it's still a statement. It has a truth value. And then there are terms, things like the city of Boston, could also be like the fictional character John Wick. Those are terms, right? They're not true or false. Boston isn't true or false. It just is. It denotes something. It stands for, it represents something in the real world. So when we talk about first order logic, we're saying that if we create a relationship between something, let's say the relationship in, so Boston is in Massachusetts, the things that are being related are terms. And then the overall statement, the relationship statement, is a sentence that has a truth value. Okay? And in first order logic, you can't relate sentences that have truth values. You can only relate terms. So that's a pretty informal and quick explanation. So that'll come up later. So let me, I've just given you some of the groundwork, and we'll talk about in a minute why that matters. Let's also mention in logic we have operators, logical operators. The things like and, or, and not are very intuitive, certainly for any programmer. These are common. But we also have the implication sign. So A implies B, or read in this prefix notation, it is implied that A, B. And I have some prior videos where I talk about how you can transform different logical expressions into one another, but I want to highlight just the implication here in order to explain why a contradiction in a knowledge base really just messes everything up. So I've got a truth table I pulled out of that prior presentation where we've got all possible values for A and all possible truth values for B. And then we show the implication sign and what the value of that statement is. So true implies true. True doesn't imply false. So there's a false entry there in the implies A, B row cell. False does imply false, but maybe most crucially, false implies true. What does that mean? Why is that the case? Well, first, you can just say, accept the logical operator. That is how it's defined in first order logic. But I also want to give you a little intuition about what implication is and why this makes sense. So imagine you've got somebody that's a little bit crazy and they believe the moon is made of green cheese. if you believe the moon is made of green cheese, then you might as well believe that pigs fly too. This is kind of the intuition. If you've got something that's false, you can believe true things. Brevity is the soul of wit was an example I used before, and it's probably true. If you believe the moon is made of green cheese and you like these little aphorisms, well, maybe you're a bit crazy, but you also believe in brevity is the soul of wit, so that's fine. So you can believe in false things or true things, but basically from false you can conclude anything. So that's the intuition, or you can just accept that that's what the logical operator means. So, does this mean complete disaster? Well, not so fast. There are alternatives, right? So in some sense, this is true. A contradiction does destroy everything, but you don't have to create one of those contradictions. There are some ways around it. So let's take, again, a very simple example of John's car is blue and John's car is not blue. Well, maybe it's actually that there are two different people that believe those things. And so if one person believes John's car is blue and you ask what color is John's car, you get the obvious answer, blue. If you ask the other person, or maybe computer or process on a computer, and the fact that's known is that John's car is not blue, and you ask what color is John's car, well, you get either I don't know, or maybe that it's not blue, or maybe a list of other possible colors or something of that sort. But there's no contradiction here. You're just asking the question of two different entities that have different knowledge or different opinions about the world. And that's okay. That's normal life. There's no inherent contradiction here as long as that contradiction is presented in context. Another thing is that people often mistake difference in labels for a difference in knowledge. So beware of this, right? So we have an American that says, I have a wrench, and then a British person says, no, you don't have a wrench, you have a spanner. Well, they name this thing differently, but their knowledge about the world is in fact the same. There's no contradiction here. It's just a different label, and obviously this holds true for somebody speaking, not just the difference between American English and British English, but Spanish or Chinese or any other language. They're going to have a different name for things, and that's okay, and they don't have necessarily a different model of what's true in the world. They'll both agree that there's this thing here that you use to tighten nuts and bolts. They just call it by a different name. That's not a contradiction. So here's a case that's a little bit more problematic. Let's say we have two statements. It's or two sets of statements. Each are a pair. It's 9 p.m. now, and it's dark here. Another statement, it's 10 a.m. now, and it's light here. Now, if we were to take a naive encoding of these, encode each of these very, very short 4 sentences in logic, then we'd have one statement saying it's dark here, another saying it's light here. That's a contradiction. But that's not really what's being said. This is more of a linguistic issue. If we re-encode it and say at 9 p.m. it's dark here, and at 11 a.m. it's light here, then we don't have a contradiction. We just have an obvious statement about daylight and the time. But what we need in logic is something a bit more than first order logic, and that's the trouble. If people are set in using a less expressive language to represent knowledge, they can mistakenly believe that there's a contradiction when in fact there isn't. It's just that they have a very limited logic and they need a more expressive logic. So here's one possible coding as we would do it in my sumo ontology. So we'd say that it holds during the particular hour of 9 p.m. or 1700 hours for Europeans, that the attribute of this location here is illuminated. And at the same time, we can also say it holds during the hour of 10 o'clock that here is not illuminated. So that's just one possible, it's kind of a naive encoding, but at least it shows that there's no inherent contradiction. There's just an appropriate contextualization for these statements with respect to time. A little more complicated situation. Let's say we have a mother that's trying to get the little boy to eat his vegetables. And she says, you must eat your vegetables. He says, On the other hand, I won't eat broccoli, and broccoli is a vegetable. So we could imagine easily that with a simple encoding of these, that boy eats vegetables as opposed to boy doesn't eat vegetables or boy doesn't eat broccoli, we'd have a logical contradiction. But that's, again, a limitation of the encoding. It's not an inherent contradiction in the situation. What really is meant here is that the responsible mother is saying, that the son has an obligation, which is the lower left-hand formalization. He has an obligation that there be an eating performed by him where the thing transferred down his throat is a vegetable. And the little boy is essentially saying, no, in the future, so a temporal qualification, I am not going to eat broccoli, and broccoli is a vegetable. So there's no inherent contradiction, just needs a more refined, more expressive encoding of what the actual situation in the real world is. So there's no contradiction here necessarily. Only, if you use a logic that can't handle the reality of what's being expressed and how. There's also a last issue that's often not discussed, which is the difference between the kind of the theory and the practice. So what if I have a really big theory? And so my own ontology sumo is a very, very big theory, tens of thousands of terms, close to 100,000 logical statements. It's a big program. Well, what you could also ask, what if there's a bug in my program? Right? Any large system is bound to have some bugs. And so here is the infamous blue screen of death from Windows. And yet, despite this bug, probably many bugs that we were all suffering from a decade or so ago, people did all sorts of useful things with Windows. It didn't happen all the time, thank goodness. We were able to get our jobs done. There were some bugs, and when the bugs happened, well, we rebooted, or we sent a note to Microsoft and hoped they fixed it in the next release. We still got work done. It didn't prevent all actions. It just was an inconvenience, although sometimes it could be pretty severe. So here's another way to look at contradiction. So let's say I have the knowledge base at the upper left. I have P, I have not P. Well, that looks scary. I have Q implies R, and I have Q. And let's say I ask, is R true? All right, now this knowledge base does tell me that R is true because I have Q, and Q implies R, but it also has this contradiction in there. And let's say that the knowledge base is ordered this way, and then the theorem prover will probably find that contradiction before it gets to doing any useful work. It'll give you faults, but crucially, you can look at that proof and say, hey, what I asked is not in there. It's just showing me a contradiction. Well, that is a signal that's very easy to manage on an automated basis so that you report, we have a contradictory knowledge base. You don't simply report a wrong answer because of that contradiction. That's always the fear, right? Because from a false statement, I should be able to conclude anything. So if I have this contradiction, that allows me to conclude false, which in turn allows me, in theory, to conclude anything else. But in practice, modern theorem provers give you a proof. You look for the query in the proof. If you don't see the query, well, then you've got a bug in your system and you need to fix it. So it's not really that big a deal. Another thing that's often not appreciated that goes in line with this notion of, could we get useful things done in Windows despite it having bugs in the blue screen of death? If you have a really big system, theorem proving is search. And you can have enormous search trees. And all necessarily in a non-trivial system, in first-order logic, you could have things that the theorem prover has never touched, lines of reasoning, lines of argument that are simply so deep and so complicated, it's never tried them. It's never needed to try them. And if you have a contradiction, say, deep in this tree somewhere, it may never get found, and it may never bother you as you go happily about doing searches and proofs in the remainder of the theory and getting useful results. So although in theory a contradiction is devastating, in practice most contradictions, or I would say, well, maybe I should say some contradictions, don't actually cause problems. And I've seen this in practice over the past 20 years as Sumo has grown. Occasionally, when there's a new version of a very powerful theorem prover like E or Vampire, I find that running it, I get a contradiction because the prover has gotten so much faster and better that it finds something that's lurked deep in the theory for a long time. But crucially, it's lurked there undetected and not causing any problems for a long time. So the difference between the theory or the worst case and the average case, the normal case, is a very big difference. Right? So I hope this video gave you some information about understanding how contradictions in a logical theory act in practice, both how can they be avoided by having smart modeling choices about how you describe the world so you don't create a contradiction where really none exists just because of a modeling choice. And then secondly, that not all contradictions, even the real contradictions that are encoded in the knowledge base for a good reason, they don't actually cause a problem in practice, at least all the time. And when they do crop up, then it's a bug and you fix the bug. So I hope you've enjoyed this and learned something from it. And if you have, please like, comment, subscribe, and let me know how I'm doing and whether this was interesting to you. Thanks very much.